Hey everyone, this is Tai Hui. I'm a PhD student in computer science at the University of Minnesota. It's my great honor to introduce our work at CVPR 2023. In this work, we try to address the slow optimization issue of deep image player. To do so, we propose a deep random project, which includes three essential components: using random value network, cutting down network dips, and adopting an extra regularizar. We verify our proposed methods on three image restoration tasks, including image denoising, image super resolution, and image inpainting. The experiment results show that our proposed method can speed up deep image player without sacrificing its restoration quality. Deep image player is able to restore images without massive training data. It uses a deep neural network to fit a natural image. As shown in the right figure, by iteratively updating the network weights, the network could fit a clean image at some points. Also, there is no massive training data. Deep image player is good at various image restoration tasks. For example, image denoising, image inpainting, image super resolution, and so on. However, there are two limitations of deep image player that hinder its practical usage. Overfitting to noise. If we train the network for a long time enough, after some points, it will gradually restore the noise. Slow rates in optimization. The fitting process is very slow, and it often takes hundreds or thousands of iterations to restore one image. As the left figure shows, our methods can restore the skeleton of image in 1 second, while deep image player cannot do so even after 10 seconds. Similarly, on the right PSNR curve, deep image player requires more than 200 seconds to reach the peak, and then it will slowly fit the noise. In this paper, we are trying to address the second limitation. To speed up deep image player, our methods include three crucial components. We switch the optimization from the network to the input seed. Not saying we are using a random value network and then fix its weight. We never update the network weight. Instead, we update the input seed. Doing so can improve the convergence. Look at the left figure. As we can see, the gradient scales at different layers are totally different. Especially the gradients at the first few layers are very small. This phenomenon will lead to different learning speeds in different layers and slow down the convergence of the entire network. By fixing the network weight, we can address this issue. We further confirm our idea by using image regression. As the right figure shows, the blue curve optimizing seed is much faster than that of optimizing network. However, after switching the law of the network weight and the input seed, the pre-iteration cost, which is dominated by a full forward pass and the backward pass, is almost identical to that of the original deep image player. To reduce the pre-iteration computation, we propose directly cutting down the network dips. Furthermore, cutting down the lateral dips can also improve the convergence. Here, we validate our idea on image denoising. As the right figure shows, when the dips increases, the optimization time also increases. Thus, we prefer to use a shallow network. However, if we look at the PSNR, we find that the shallow network leads to low quality restoration. So, the question becomes how to take advantage of the shallow network without sacrificing the restoration quality. We suspect that the degradation in restoration quality may be due to the fact that Optimizing the input seed with the frozen network dramatically surpasses its implicit player. Therefore, to bring back the restoration quality, we propose employing additional players. In our paper, we employ total variation due to its popularity for images. So finally, we have our regularized version of deep random project. We test our methods with two different network architectures. The first row shows the deep image player-like architecture. The second row shows the deep decode-like architecture. We first conduct our experiments on image denoising. We are given a noise image Y with additive noise. Our goal is to restore its underlying clean image X. The objective function can be formulated as this. The right figure shows the visual comparison of our methods, deep decode and deep image player. Visually, the restoration quality of all methods looks similar to the best model deep image player, suggesting the restoration quality capability of our methods. We further evaluate our methods on a popular image denoising datasets and report the performance. As we can see, in terms of image restoration quality, our methods achieve competitive PSNR as that of deep decode and deep image player, while in terms of optimization time, our methods show a significant advantage over them. We then conduct experiments on image imprinting. We are given a noise image Y and the mask M. Our goal is to restore its underlying clean image X. The objective function can be formulated as this. The right figure shows the visual comparison of all methods, deep decode and deep image player. Visually, the restoration quality of all methods looks similar to deep decode and deep image player. We further evaluate our methods on an image imprinting dataset and report the performance. As we can see, although deep decode and deep image player eventually might catch up our methods. However, if we look at the however, our methods show stronger advantage over them regarding the speed, especially if we look at the comparison in the first 30 seconds. In this paper, we investigate the slow optimization issue of deep image player. We propose a simple yet effective method around the deep random project to speed up deep image player. We evaluate our methods on common image restoration tasks and verify its effectiveness. Thank you. Have a good day.